Hi there, students. This is Dr. John, your physics and math professor, and today we're going to be looking at heat that comes from an electric radiant heater, and we're going to look at the heat whether it's upside down or right side up and see if it makes any difference. So I've written out the problem for you in the bottom of the screen. I'm also going to read it off for you right now as well. Electric room heaters use a concave mirror to reflect infrared or IR radiation from hot coils. Notice that infrared light follows the same laws of reflection as visible light. Given that the mirror has a radius of curvature of 50.0 centimeters and produces an image of the coils 3.00 meters away from the mirror, what is the magnification of the heater element? Notice that its large magnification helps spread out the reflected heat. So I've tried to draw this up for you. Hopefully the picture makes sense. So here we have a heater element. Think of this as like a concave or like a half or a quarter of a circle of a piece of metal, and then there's a red hot heater rod inside there, and it reflects light like this. So here I've drawn, this would come out like this, sort of like I've shown here. It would come out like this, maybe, like 2 or 3 feet out like this, and there's a rod, a hot element that's here in the middle, reflecting light over here and producing an image that you're going to feel. You're going to feel the heat because it's a real image. You're going to feel it over here. So let's follow this and see what happens. The light from this would enter this cave. So this is called a concave mirror, and it'd be a piece of metal that's painted so that it's highly reflective. So it'll enter this concave, and then it would tend to come toward the focal point. If you had a ray of light coming here, it would tend to come toward the focal point. So it's a converging mirror. Anytime you have a concave mirror, you also converge. Just think quickly of what the light would do. Would it come toward a point? If it does come toward a point, then it's converging. Let's look also at the sign convention here. This distance here, from here to, we normally measure it right here to where the mirror hits here. This would be a positive distance because light's coming from there, just as it should be. And then this distance here to the image is a positive distance because light should reflect and images should form on this side of the mirror. So this distance is positive because it is where it should be, and the focal length from here is a positive distance because light's actually focusing in on that. Or think of it, if you think about converging mirrors or converging lenses, always have positive focal lengths. So now let's take a look at this problem over here. We said that the distance to the center of curvature, which is like this, is 50.0 centimeters. That's 3 significant figures, which we want to convert to meters, or 0.5 meters. So we'll have 0.5. I didn't put the 3 significant figures in there. We'll do that in our answer as well. There. And then we want to find the distance to the object. Now here we're going to use the lens formula for that. This is the magnification formula. Now notice here, I've just written this as an object. Sometimes people go DO for distance to the object, and this would be DI. Sometimes they'll just write I. So notice here I use DI, distance to the image, distance to the object. I could have just written I and O as well. So just not to confuse you, but I've put both of them there because you'll see both of them in your different kinds of problems as well. So here's our 2 lens formulas. Let's use this lens formula here to find the other thing that we're going to need, which is the distance to the object. Well, over here, we remember that the focal length for a thin mirror or a thin lens is always half the distance to the center of curvature. The distance to the center of the curvature here is 50, or 0.5. So the focal length or the focal distance is going to be 0.25. So I just already wrote that in here. I wrote that over here too. So the distance to the image is 3 meters. To the focal length is 0.25 meters. And we want to also find the distance to the object because we're going to need that for the magnification. So I used our lens formula here. 1 over the distance to the object. We don't know what that is. We don't know where the object's going to be. Plus 1 over the distance to the image, which is 3, is equal to 1 over 0.25, the distance to the focal length. And if I sort this all out, I'll have to use my calculator for this. I'm going to get O is equal to 0.2727. So this over here, O, I'll just write this in here, is 0.2727 meters, of course. Now, if you notice here, since this distance here is 0.25, from here to here is 0.25, our object is actually just outside the focal length. So it's going to be right around here somewhere, very close to the focal length. Now, you may remember from some of our previous videos that for converging mirrors or converging lenses, as your object gets closer and closer to F, your focal point, your image will get further and further away. It's going to still be a real image if you're coming from this side, but it's going to get further and further away, and it's going to get bigger. The magnification is going to get bigger. And we're going to see that in a second here. So our distance here to the object is just outside the focal length here. And we want to find the magnification. Remember, the magnification is the image, the distance to the image over the distance to the object. And I've written here the distance to the image is 3. Remember, it's positive because of our sign convention. The distance to the object is 0.2727, which is right there. And I calculate and I put that minus sign in front of there. We need that because of the geometry and because we want to be able to create this upside down image here. So we have to put that minus sign in there. And the answer is going to be minus 11.0. That's going to give me 3 significant figures, just like I had here and just like I had here for these different parts of the problem. So the magnification is 11. So that means the height of this thing here is 11 times this. So I'll try to draw that into perspective here. So if this thing is this height, 1/11 of that might be that height right there. Teeny tiny. As we said, we get closer to F, we're going to get a much bigger image over here. So the magnification is going to be 11 times, it's going to be inverted, it's going to be negative. So it's going to be like whatever the picture is that you have here on the element. If you had a picture on the element, it's going to be flipped upside down here. And will that make any difference? It's still going to feel just as warm here if this was this way or if it was this way. It's a real image, so it's actually going to feel warm, and it's going to feel just as warm if it was an inverted image or upright image because it's still heat. It's still infrared heat. You don't have to look at a picture for heat. It doesn't really matter. Upside down heat is still hot. And it's going to be a magnification of 11. So however big this coil is, let's say it's this big, it's this coil that may be an inch or a couple of centimeters in diameter or something. This is going to be, let's say it's 1 inch in diameter. This is going to be like a foot in size here. Because if this was a smaller image than the object, it would get so hot here it would burn you. So what they try to do is spread the image out from the coil so that you feel warm over a much bigger distance. So I hope that helped to take a look at upside down heat here. And if it did, like and subscribe, and I will see you in the next video. Bye-bye.